let's move on to our afternoon section. So each team, please introduce yourself. Let's start from the reporter.
Hi, we're Team Excel, and I'm Hong Xiangling. This is our Captain Hong Yiting. This is Yang Xingru. This is Xiao Yu. This is Wang Xuanxi. And we're looking forward for a good discussion. Thank you.
Opponent.
Good afternoon, everyone. My name is Jonathan Bruce. I'm the captain of the Taipei Medical School No Nighters. This is my team. This is Richard, Jason, Ryan, and Eva.
Reviewers.
Good morning, honorable jury and fellow members. We are from Taiwan First Senior High School, and our team name is Team S502. And my name is Gu Xinyu. He is Deng Wenmin. He is Chen Zhiren. He is Wang Yuan. He is Tian Yichen. Thank you for everything.
Okay, then jury, please introduce yourself. My name is Xia Wei from National Central University.
My name is Hong Weiqing. I come from military academy.
I work for the National Taiwan University of Education.
来自中正大学。
周方玉from National Taiwan Normal University.
Okay, so the opponent, please challenge the reporter for the problem.
已经选好了。
Oh, sure. Okay. Then, please, each team please write down the representatives' name. 第五场是就选他最好的就对了。
可不可以有一张空白的纸？
I
reporter from Texas South. Good afternoon. I'm the reporter from Texas South, and today I'm going to report number 9, soy sauce optics. And here's cover statement. Using a laser beam passing through a thin layer about 200 micrometers of soy sauce, the thermal lens effect can be observed and investigate this phenomenon. According to the cover statement, our main focus should be on why will thermal lens effect happens and what parameters will influence this phenomenon. And here's my outline. On observation, I will show you the differences between with and without soy sauce layer so that you observe the thermal lens effect. Then in theory, I will tell you how thermal lens effect happens on soy sauce layer. Then I will show you my equipment and the software we use for my experiment. And then I will use 3 parameters to investigate this phenomenon in the experiment. And finally, we can get some conclusion. And here's observation. In observation, we'll try to find the differences between with and without soy sauce layer. And for a left picture, laser beam hit the paper screen directly without hitting the soy sauce layer. But for a right picture, laser beam hit the soy sauce layer first and then hit the paper screen. And from these pictures, we can know that the one with soy sauce layer, the spot is much bigger than the one without. So we can say that the thermal lens effect happens on the soy sauce layer. And here's the theory. To introduce the thermal lens effect, first we need to talk about the laser beam. Actually, laser is kind of Gaussian beam, which intensity I keep changing in cross-section area when the radial distance means r as difference. And this is a formula of the Gaussian beam. And since the I0 means the intensity of in the middle of the soy sauce, and the width of beam means W, is the same. So actually, the intensity of laser beam in cross-section area is kind of called projective function. So when the soy sauce absorbs light and turns into heat, the delta T in each part of the soy sauce is also a projective function. So now we know that the delta T in each part of the soy sauce is not equal. So when the soy sauce absorbs light and turns into heat, the refractive index of each part in the soy sauce is also not equal. And because the thermal optic coefficient means this is negative, of soy sauce is negative. So after laser passing through the soy sauce, the refractive index of the middle is smaller than the other part, just as these pictures show. Therefore, soy sauce becomes a diverging lens. And this is another formula which can help us calculate out the focus length later in my presentation. And later on, we will focus on the relationship between the focus length and F focus length and B means absorption coefficient of the liquid, and N0 means the refractive index of the liquid. And these are the equipment that I use for my experiment. First, we have a soy sauce layer. I use 2 plastic as the outer layer. Then I put 200 micrometer plastic and some soy sauce between the outer layer. So when I staple them together, just like this picture shows, the soy sauce layer is the thickness of a soy sauce is also 200 micrometer, and for this corresponds to the problem statement. And also we have a thermal image camera to help us measure the temperature of a soy sauce, and the temperature will show on the cell phone which is connected to the thermal image camera. Then we have a normal convex lens to help us calculate the focus length later in our experiment. And instead of a normal laser beam, we have a high-power laser, and which can that the thermal lens effect happens later in the experiment. And here's the setup. First, we have the laser beam as the source of the heat. Then we have a soy sauce layer, which will become a diverging lens after laser passes through it. And third, we have a paper screen so that the laser imaging on that. And finally, we use a camera to record the image we got from the paper screen. And this is what it really looks like from right to left. We have laser, and we have a soy sauce layer. We have a screen, and we use camera to record the image we got. And this is the software we use. We use ImageJ to analyze the spots to analyze the result we got. And after draw a line across the spot, we can get great value of the image. So, yes. And in order to know whether thermal lens happens or not, we need to observe the change of the spot. So we need to have a very clear definition of the spot. And so we define that the area which bright value is more than 150 as considered in the spot. So when we know the So now we know the spot size, the diameter of a spot, then we can know that whether thermolens happens or not in our experiments. And these are parameters that I use for my experiments. First, I have compared the soy sauce and the water to see which one can have the thermolens effect. And second, we change the exposure time from 2 minutes, 4 minutes, 6 minutes, and 8 minutes to 10 minutes. And that means the time that soy sauce under laser exposure. And finally, we change the concentration for soy sauce. We add water to the soy sauce. So the concentration varies from 20%, 40%, 60% to 100%. And this is again this is a setup for our experiments. We have a laser and soy sauce and paper screen and camera used to record the image we got. And next, I'm going to talk about experiment 1. In experiment 1, we compare the soy sauce and water. Although the product statement should focus on soy sauce, but we think it is also quite important for us to know the differences between the soy sauce and other liquid. So the control variables for this problem, for this experiment, is a laser power supplement, and the parameters is the liquid and the layer, which is soy sauce and the water. And these are the pictures that laser passes to soy sauce and water for 4 minutes. And from these pictures, we can see that the soy sauce, the one with soy sauce, is a little bit bigger than the water. So we can say that the thermolens effect happens on the soy sauce. And this is the result we got from experiment 1. We found that for soy sauce, while exposure time increased, the spot size did increase, the orange spot did increase. So we say that the thermolens effect happens on the sauce layer. But for water, we found that when the exposure time increased, there is no obvious change. The blue side, there is no obvious change of the spot. So we say that the thermolens effect did not happens on the water, and we think that's because water is a colorless liquid. It cannot absorb light and turn into heat. But a soy sauce is a darker liquid. It can absorb light and then turn into heat, and then happens thermolens effect. Then experiment 2, we change the exposure time, and that means the time that soy sauce under laser exposure. And the control variables for this experiment is a concentration, which is 100% soy sauce to do the experiment, and also the laser power supplement. And our laser power supplement is powered by a DC power supplement. At first, we choose the battery to be the power supplement, but we found out that the battery is not steady enough, so we choose DC power supplement to be the power. And then parameters for this experiment is exposure time from 2 minutes to 10 minutes. And in order to have a deeper investigation for this problem, we'll try to measure the focus length of the surface layer. And first, we put the LED light right on the focus of the abnormal convex lens. So when the light goes to the convex lens, it becomes a collimated beam. We did not choose laser to do the experiment because, as we know, laser is kind of a Gaussian beam which will diverge since its propagation. So we choose LED lights to be the beam. And after, when the collimated beam goes to the soy sauce, it will diverge again since the soy sauce layer is divergent lens. And then we can calculate out the focus length of the soy sauce layer. And that's what it really looks like. And then experiment 2, since the parameters for experiment 2 is exposure time, so we think it's also quite important for us to know the temperature of a soy sauce. When the exposure time is 2 minutes, when exposure time is 2 minutes, the temperature is 30 Celsius. But when the exposure time is 10 minutes, the temperature is about 55 Celsius. So we know that when exposure time is increased, the temperature will also increase. And this is the result we got from experiment 2. We can see that when exposure time is 2 minutes, the focus length of the soy sauce is 250. But when the exposure time is 10 minutes, the focus length is only about 150. It's about 150. So, and that's because, as we know, when the exposure time increases, the temperature of the soy sauce will also increase. And according to the, because the thermal optic coefficient of a soy sauce is negative, so the refractive index will increase. And then, according to the formula from our experiment, we found that when the refractive index decreases, the focus length will also decrease. So we connected our theory and the experiment. And last experiment, we change the concentration of soy sauce. And the control variables for this is these, and the parameters is the concentration of soy sauce. And because the concentration of soy sauce will affect the transparency of the liquid, so we know that according to the Beer-Dangle law, absorbance equals to the density of the liquid multiple absorption coefficient multiple thickness of the layer. So concentration will also affect the absorption coefficient of the liquid, which is one of the important factors for us to calculate the focus length. And after measuring the transmitted and incident light, we know that we found that when the concentration is 20, the absorption coefficient is only 0.1. And when the concentration is increased, the absorption coefficient will also increase. And because the darker the liquid is, it's easier it can get light. It can absorb light. So we also find out that there's a very close negative correlation between the focus length and the absorption coefficient, and that corresponds to our theory. When the coefficient is higher, the focus length will decrease. So there's a result from experiment 3. We can see that when concentration of soy sauce is 20, the focus length is 800. But when the concentration comes to the 100, then the focus length is only about 200 centimeters. So that is because when the concentration is higher, the absorption coefficient is higher. Because the darker the liquid is, the easier it can gather light. And according to the formula in our theory, we can know that the focal length will decrease. So we connected our theory to our experiment. And here's a conclusion for my presentation. And from theory, we know that because the thermal optic coefficient means that dNdt is negative. So after laser passing through the soy sauce, it becomes a diverging lens. And there are two ways to increase so that the thermal lens effect become more obvious. And the first way is to increase the exposure time. When we increase the exposure time, the temperature will increase, and the refractive index of soy sauce will decrease, and then the thermal lens effect will become more obvious. And for the concentration, when the concentration is higher, and then it's easier to absorb the light, and the absorption coefficient will become higher, and the focus length will decrease. That means that become more obvious. That's all my presentation. Thank you.
Please ask a question.
Okay, so could you go back to your graph for the absorption versus focal length? Yeah. So for that one, could you please explain why there is a constant in the denominator of the fitting equation here, whereas a constant is not here in there? So why is there the negative 0.62 constant? Can you explain that?
I think that is because the concentration, the absorption coefficient, and the focus length is not totally like negative correlation. So, but the only 0.6, I think that is very small. So I think that is acceptable. Yes.
Okay. And could you go back to the previous graph?
Yes.
Okay. So I just wanted to clarify. Do you think this trend is actually linear, or is that just the best fit line that you have put in there?
I think it is linear. Yes.
Okay. Another question I have. So you already mentioned that you used an LED light for measuring the focal length over time.
Yes.
Because it allowed you to get rid of any problems with the Gaussian beam. So do you think that this would impact your results? Do you think that you would get different results if you use the LED versus the laser to perform this part of the experiment?
No, sorry, I think it won't affect because we measure the focus length with LED light right after soy sauce was hit by the laser. So it won't affect the result. We just use LED light to measure the focus length, but we use laser beam to hit the soy sauce.
Okay. No further questions. I'll save the rest for the discussion.
Thank you.
Separation of the movement. Opponent takes the floor.
Okay, so good afternoon, everyone. My name is Jonathan Bruce, and I'm the opponent for omitters. I will be opposing soy sauce optics. Okay, so let's begin with the problem statement here. Okay, so the problem statement reads, using a laser beam passing through a thin layer about 200 micrometers of soy sauce, the thermal lens effect can be observed. Investigate this phenomenon. So I feel that some key parts of this problem statement are the thin layer, which is about 200 micrometers. I feel that the reporter controlled this well in their experiment, as well as the thermal lens effect, and defining exactly what the thermal lens effect is. Okay, so here's how I think a problem-solving outline should be done for this. So I think first there should be a phenomenon investigation. I think the reporter did this quite well, going through all the qualitative description of the phenomenon. Then I think there should be a discussion of relevant parameters, as well as a model and experimentation. So first, allow me to congratulate the reporter on some of their strong points. I liked how their observation slide was very clear, and they very intuitively defined the phenomenon and thermal lensing. I also like how they had a clear explanation of theoretical concepts and assumptions, for example, the Gaussian beam, TYPT, and the focal length, and how they controlled their experimental parameters, especially the thickness of the soy sauce, quite well. And this also goes for their experimental setup. It was very clear. And they also described how they used image J to analyze the beam. And they also had a fair range of parameters. They tested exposure time, concentration, and comparison with water. Some things that I think they could have improved on is, first off, a theoretical basis for why n changes, why dn dt is negative, and also potentially accounting for the effects of thermal expansion in the theory. I think that they could have improved their theory and the qualitative explanation in terms of that. I also feel that they should have included theory curves for their experiments. All of their graphs were only described qualitatively or through regression analysis. Speaking of that, the regression fitting does not appear to have a theoretical basis to it. For example, as I already pointed out, there's a constant in the bottom of one of their regression fittings, and another one is linear but without theoretical backup. And also, again, I noticed that their temperature increased significantly. So I feel that thermal expansion is an effect that should be considered in the theory that they are proposing for this topic. So for my discussion, I will start by going over some intuitive theoretical explanations, and then I will move on to some of their experimental data. So I'd like to lead into the discussion. Okay, so I'd like to start with a bit of intuitive explanation for your theory. So could you provide for us a reason why the refractive index would change at all when the soy sauce is heated? Just an intuitive explanation for why n changes.
And I think it's because the polarity of the soy sauce and difference when the heat goes to when the soy sauce absorbs the heat.
Okay.
The polarity. I think the main point is not the thermal expansion, because as we know, while the temperature change, the density of the water or the soy sauce naturally a lot. So I think the density is not the main cause. The main cause of this one to happen.
Okay, I actually would like to agree with the point about polarizability. However, I slightly disagree with their point on thermal expansion. I do feel that since their laser was very powerful and their temperature of the soy sauce increased significantly, if you look at the graph,
and there's density of water changes the temperature. And as we know, soy sauce as water soy sauce it has a lot of water. So
Okay.
from this part we know that while temperature changes from 20 to 60, in our experiment the temperature changes from 30 to about 55. But you can see that the density did not change a lot. It's about 1%.
Okay.
So we think that is like that.
Okay. Yeah, I do agree that the change would be very slight. I still think it would be a good idea to consider it. But I do agree with your point on the polarizability. Do you have a theoretical explanation for why d and dt would be negative? Have you calculated this value theoretically?
Because just like what I mentioned, when the soy sauce absorbs light, and there is a thermal fluctuation of the soy sauce, so that the light can go through the soy sauce quickly, so that refractive index will decrease.
Okay, but have you actually been able to calculate a theoretical value of d and dt?
I would think that is difficult for us to calculate that.
Okay, then have you been able to calculate it experimentally?
We try to do that, but we found out that it is also too difficult for us to calculate that. But I think that is also okay.
Okay, so I think that maybe the reporter, if possible, should try to obtain a value for d and dt, either theoretically or experimentally. I do know of one equation that might help with this theoretically, which is the Lorentz-Lorenz relation. This can be derived from the Boltzmann distribution as seen in several papers. And I believe the equation goes something like this. N squared plus 1 over N squared plus 2 equals 4 pi over 9 times N squared over 8t. So as you can see, this equation relates N to t, and I think that you could use this to calculate theoretically. Additionally, if you want to do it experimentally, I would suggest using a simple handheld refractometer.
Thank you. That's a great suggestion. Thank you.
All right. Next, let's see. Okay, I would also like to ask if you think that d and dt is constant for any given temperature.
And I think that's not constant.
Okay.
Yes.
So what do you think will happen to d and dt as the temperature increases?
And I think that depends on what has a range of the temperature.
Okay. So I would like to agree with the reporter on this point. I do also agree that d and dt is not constant in temperature. Okay, so additionally, so let's go back to your comparison between the soy sauce and the water.
Okay.
Yeah, so even though water does not have as high of an absorbance as soy sauce,
Yes.
Water still does absorb heat. So how could you explain the trend of water not exhibiting the thermal lensing effect?
I think water may absorb the heat a little bit, but in our experiment, we just exposed this being for about 10 minutes. If the exposure time is much longer than 10 minutes, I think that might happen, but just a little bit, not
Okay.
that much.
Yeah, I would like to agree with the reporter's explanation. I was just asking that question as clarification of whether we thought it was occurring at all, or whether it didn't occur. Okay, so also I would like to ask another question. So what do you think would be the impact of the wavelength of the laser on the thermal lensing effect?
I think if the wavelength of the wavelength is like shorter, the thermal lens effect becomes more obvious because the intensity of the light is not the same.
Okay, I think that is a very valid point. Actually, the absorbance for soy sauce is much higher at blue and purple wavelengths, so I think that is a good point right there. Okay, so now let's move on to your experimental results. So I noticed that for all of these experiments, you do not seem to have any theory curves. So could you please explain why you didn't include the theory curves in the graphs? So for example, this one, also your focal length versus.
For this one, because the water do not have the thermal lens effect, so we cannot cannot calculate out the focus length from our experiment. So that's why we did not put a theory line on it.
Okay,
Because
but
we
it's-
cannot calculate out.
Okay,
Yeah.
I was just referring to your graphs in general. I mean, like in general, your graphs only seem to have qualitative comparisons with the theory. So is there a reason why there are no like three curves? I mean, like, could you go to some of your like, graphs after this? Yeah, for example, these graphs. So why are there no theory curves?
I think that's we try to measure the focus length we try to measure out these like K, like W, but we found that it's very difficult for us to found that because that K is the thermal conductivity of the liquid, and we found that it's very difficult for us to measure that, so we did not do that. And we tried to do that, but we did not successfully do that.
Okay, so I agree that might be difficult. I still think that that maybe you should try to include a theory curve. Since you mentioned soy sauce is mostly water, maybe even for the thermal constants, you could approximate the values using water. But I think it would be a good
Okay,
idea to
that's
include
good
theory
suggestion.
curves
Thank
in your graphs. Okay, so let's see here. Okay, so another point I would like to bring up would be thermal diffusion. Do you have any equations or simulations that would model the temperature at different points on the soy sauce? Because for the laser, unless I have some misconceptions about your setup, the laser only hits one part of the soy sauce, it doesn't hit the whole thing, right?
Yes.
So do you have any equations to model thermal diffusion and how this would change the focal length of the soy sauce and therefore your image?
I think if the laser just shot the soy sauce for only one part, it also have similar effects because the heat goes outer, so it also will have these kind of temperature. So that will cause similar effects. Yes.
Okay, I think it would be a good idea to possibly include thermal diffusion in there.
Okay.
Maybe just for future work. Okay, so one of my final questions for this discussion would be, what do you believe is the most important parameter that you have tested in terms of like driving the thermal lens effects? So what characteristics of your experiments and of the theory do you think are most important in causing the thermal lens effect to occur?
I think the darkness of soy sauce is very important, as the darker the liquid is, it is easier to obtain light. Yes, and another factor is the laser beam, because the laser beams have a Gaussian beam. So I think that's also very important for this phenomenon to happen. So
Okay.
laser beam and the darkness of soy sauce.
Okay, I would like to agree that concentration, due to the changing absorbance of the soy sauce, also, I would like to agree that this is probably the most prominent factor in the experiments. With that, I would like to conclude this session. Okay. So I feel that the reporter and I had a very fruitful discussion just now. So a couple of key points. First, we discussed intuitive explanations for why the index refraction changes, and also for measuring or calculating DNDT. I feel that the reporter did a good job of explaining why n changes. But I also feel that they could have done some work to calculate DNDT, either theoretically or experimentally. We also talked about thermal diffusion, about whether DNDT is constant or not, the impact of the laser wavelength, and also why the thermal lens effect does not appear in water. We also addressed the reporter's lack of theory curves. I think that they could improve on this. Thank you.
Reviewer, please ask questions.
Okay, so pertaining to the phenomenon itself, do you think there's any other factors that would also affect the phenomenon itself? Like any other than polarization or such as the density as in component attacks?
I think the thickness of the layer will also affect, just as this in formula, L means the thickness of the layer. So I think thickness of the layer will also affect this phenomenon.
Okay, so how about the opponent? Do you think there's other major factor that could also affect the phenomenon?
I think in terms of impacting the change in index of refraction, I would like to stand by my points of polarizability and thermal expansion.
And thermal expansion. I agree. And so, like, accordingly, as the do you think that the intensity of the laser would affect your experimental data?
Yes, because at first we used the laser pen, normal laser pen. And we found that the intensity of that is not enough for the stimulus effect to happen. So later on we have a high power laser and that can get the stimulus effect. So the intensity will definitely affect the phenomenon.
Okay, so another one. And you use, as you mentioned, that you actually does the experiment by first using a laser beam to heat up the solid salt layer, right? And then use the LED. So do you have make a graph on after you heat up the layer and you use the LED to pulse on it? And do you think that do you have a graph on what's as the time goes by, what's happened after you heat up? Like it's going to cool down, right? Or it's the
You mean the temperature of the?
I mean the thermal distribution inside the layer.
We did not do that, but we think that not affect a lot because we light the laser. We use the LED light right after the laser beam, so we think that is very similar to this.
Okay, so
I think that won't affect a lot.
and another for clarification. So how do you actually measure your temperature?
Oh, I use thermal image camera, just like these thermal image camera.
Oh.
Temperature will be shown on the cell phone that's connected to it.
Okay, so next is for the component. So do you think that how would this thermal diffusion affect
I think that thermal diffusion could be important because it could cause an actual gradient of index of refraction, and this could bring in such phenomena as constructive and destructive interference when the beams of light refract differently.
Okay, and just like one more.
Oh.
So how do you think the laser wavelength would affect the phenomena?
I agree with the reporter's explanation. I feel that lower wavelengths of light will cause the phenomenon to occur more clearly due to the absorbance characteristics of Swiss sauce.
Preparation of the reviewer. Reviewer, please take
This is young one.
So honorable G and fellow commentators, so the review today from the DMS Institute. So we're going to quickly give an overview of the problem statement. So the problem statement is stated here. So my main focus, which is the same as the reporter and opponent. So let's give an overview of the presentation. So at the first part, the reporter gives us an observation of the phenomenon, which they give a clear introduction about the phenomenon on various pictures, and then the theory part. But they actually did not provide a very clear definition on the thermalized effects only after a discussion between the opponent and we get to know what is exactly the phenomenon was about. And next part, in the equipment and software, they did a clear explanation on set out and how they control the parameters. But I believe that there's still things that to consider as the effect of glass or plastic layer they keep on the layer of the soy sauce. And next part, the experiment. So though they have done a great work on measuring the experiment and discussing how the tendency of the parameters and variable related would work, but I think there's too many parameters tangled together. As like one with the focus length, there are so many tangled together and so many parameters that are changing at the same time, which gives us a little bit difficulty on trying to read how the information actually works. And in the last part, the conclusion, they clearly conclude that this research, but I believe that just as the opponent stated, there are still other possible effects that I think that the reporter could have done more further discussion on it. So let's take a look at the opponent's pros and cons. So I think the opponent has done a great job in giving suggestions to the reporter to improve its comprehensiveness in the whole theoretical explanation and further presentation. And they make a precise control on prioritization, which I think is a very good idea to ask the question, which helps us to clarify what the phenomenon is. But in cons, they did not use all the time, which I consider you could prepare more problems, which would make makes the discussion more interesting or more in the aspects of physics. And they did not actually consider a lot of the effects in the parameters of the soil, such as the reporter they just give you the parameters of the density change, the difference between density on the temperature, based on temperature, but they did not actually give you parameters regarding the soil source. So I believe that there's actual difference between them, so it actually could give another phenomenon through the thermal expansion. So let's take a look at the discussion section. So first, the opponent asks that why would the density of water change? Would the density of water change affect the result after heating? And the answer from the reporter is water is only heated a little and density won't change enough. And as I mentioned, I believe that actually you only give us the parameters about regarding the water, but I believe that you should also give us the related parameters through the soil, so that we could actually compare them to each other, so we could know the precise answer of this question. And next part, so how do you calculate the NDT, or how do you know it's positive or negative throughout the whole phenomenon? So they say it's too hard to calculate, however, it would change with the temperature. So as we at least know this was not a constant number, and they also did not, I think that would be great if they had done a more precise explanation, description on how the value of the NDT would work in different T, for they could even or make a graph of it. It would be a lot better for their presentation. And the next one, what is the most important parameter in this experiment from the opponent? And the darkness of the soil source and the intensity of laser beam.
And there's a conclusion report for the reporter. And first, ESL device is used to measure the focus depth after the experiment. So the soy sauce is heated by the laser, so I think it won't affect the results. We just use LED light to measure the focus depth. And another part, dn over dt is not a constant. It depends on the temperature. But the range of the temperature is not the same. The dn dt is not the same. And also, water density won't change a lot in our experience. And since the soy sauce is mainly composed of water, so its density won't change a lot too. So the opponent just thinks about the thermal expansion. I think thermal expansion did affect a little bit, but not that much, because the density won't change a lot in our experiments. And also, water could absorb the heat if the exposure timing increased, because I think water is not actually quite pure. So it can absorb the heat, but if you want to absorb the thermal effect on the water, the exposure timing that have to be very long, but that is impossible for our experiments. And the darkness of the soy sauce and the laser bean are important. The darkness of soy sauce means the concentration of soy sauce. When the concentration is higher, the darkness it is easier to absorb light, so it can have thermal lens effect. And laser beam, because the Gaussian beam, because laser is kind of a Gaussian beam, so it can have thermal lens effect to hackers. And further parameters are thickness of the layer, and the thickness of the layer will influence this phenomenon. And intensity, I think intensity will affect the phenomenon. So we use DC power to ensure that the intensity remains not powered by the battery. And the reviewer just said that we did not have a definition of thermal lens effect, but we did. I will say that in my presentation. I say that in order to know whether thermal lens happens or not, we need to have a very clear definition of the thermal lens effect, and that means the change of a spot diameter. Thank you.
Any questions from you?
I got a question for three of you. It says that three of you all agree that the dA over dt is not constant. But my question to you is that based on the experimental result, what made you think it's not constant? Start from the reporter.
I just say reference that the differential index change with temperature is not that thing. It's like this. So I think the details.
The base of your experimental result.
We do not fit our experiment into this, so but I see a reference about that. So I know.
I would like to agree with their assumption that things like this, I think this can be verified by using that equation that I proposed up there. That's how we calculate it.
I totally agree with two of them as the references, and a lot of comparison I've seen is like comparing it to a non-linear lens. So I agree that there must be a different, in a different temperature.
One question for all three terms. Actually, it's two. So the reporter mentioned that the laser beam is Gaussian. So the first question is that is it really Gaussian beam for the laser? So start from the viewer.
I think it's a great assumption. If it's not.
Do you think it is? Do you think it is?
I think yes, potentially.
Yes, I think it's a Gaussian.
So
Yes, I think there's also.
okay. Secondly, is it important that, or is it really that only Gaussian beam will induce this kind of thermal lens effect?
Yeah, I think if you use LED light and then when we hit the soy light in the spot, then it goes out.
Yeah, but I mean, what my question is it only Gaussian beam
No.
that will induce thermal lens effect?
No.
I think no, because but it's one of the most effective ways, since that the little red spot from laser beams will actually easily create the different spot which contains the different thermal energy.
I agree with the reviewer. So I feel that Gaussian beam would be the best because it would create the most pronounced thermal diffusion gradient, and we saw the impact of temperature on the index of refraction. So I feel it would be the best. However, I also don't think it's the only way because a similar gradient can be created by a non-Gaussian beam.
Any other question? Okay, so let's give Yuri 1 minute to score.
5 minutes.
No, 5 minutes? Okay, 3 minutes. 5 minutes.新的，以前我差，但是没有这段时间。因为以前。对。
primarily.
Okay, so for the recorder, 89886. And for the opponent, 88887.
Thank you.
For the reviewer, 78886. Okay. So we finish this section. And please come back after 15 minutes. Those are stage 2. And so the problem is number 14. And all teams, please write down your name on the board. And the reporter is preparing the presentation.
Good afternoon, honorable judges and fellow physicists. My name is Ethan Wu, and today I'll be presenting on the looping pendulum phenomenon. First, I'll start by introducing the phenomenon and going over some of the qualitative principles behind it. Then I'll move on to showing how we derived our equations of motion for the phenomenon. Then I'll share some of our experimental findings, and finally conclude with a discussion of the comparison between our data and our theory. So first, the problem statement reads: connect two loads, one heavy and one light, with a string over a horizontal rod, and lift up the heavy load by pulling down the light load. Release the light load, and it will sweep around the rod, keeping the heavy load from falling to the ground. Investigate this phenomenon. So as you can see in this video here, when the light load is released, at a certain point around this vertical, the heavy load stops falling. So our focus for this problem will be in investigating why this process occurs. What are the forces that are stopping the heavy load from falling? And what are the parameters that affect this process? So qualitatively, we know that there is a downwards force on the heavy load caused by gravity, and that this is the force that is causing the system to slide to the right at the beginning of the phenomenon. At the same time, the light load falls down, entering circular motion, and the tension force from the rope pulls upwards on it, creating a centripetal force. As the heavy load continues to fall, the radius of rotation for the light load decreases, increasing the centripetal force. However, from Newton's third law, we know that just as the rope is pulling inwards on the light load is also pulling outwards on the rope. So from this, we know that there's a resistant force to the falling of the heavy load. There's also friction existing between the rope and the crossbar that also opposes the sliding of the system. So together, both of these forces increase as time progresses, eventually equaling and matching the weight of the heavy load and causing the system to decelerate, then stop. We can also derive a quantitative theory to better model this phenomenon. There's a few assumptions that we made. The first one is that the rope is inelastic, or that if you model it as a spring, the spring constant approaches infinity. The second assumption is that the heavy load has no tangential motion, meaning that it moves strictly up and down. The third assumption we made is that there's no drag force. The reason we made this assumption is that experimentally, the loads that we used were up to 1 kilogram in weight. So the any effect due to drag force is relatively small compared to this force. And finally, our assumption is that the rope is massless. I'll be going into more detail about this final assumption later. Very briefly, this system has 2 degrees of freedom, so we chose 2 coordinates to represent it. There's theta for the angle of contact between the rope and the crossbar, and there's h for the vertical displacement of the heavy load. However, in our derivations, we found it convenient to introduce a third variable r to represent the radial displacement of the light load. So for this, we also introduced a constraint equation based on the inelastic nature of the rope and the fact that its length is constant. Now we can do a force analysis. So if we look at the heavy load in the vertical direction, there's the weight pulling downwards and the tension from the rope pulling upwards. In the tangential direction, as we assumed earlier, there's no net force, so no net acceleration. On the light load in the radial direction, we see one component of the weight pulling outwards and the tension force from the rope pulling inwards. And together, these 2 forces must account for both the actual movement of the light load as well as the centripetal force needed to keep it in its circular path. In the tangential direction, we see the final component of the weight of the light load acting on it tangentially. The last force we have to model is the friction force between the rope and the crossbar, and we can do this through what is called the capstan equation. The capstan equation basically takes a look at each infinitesimally small segment of rope and sums up the tangential and normal forces acting on it. We can do this through integrating the system of differential equations, arriving at this result. What this basically tells us is that if we pull with a force of T1 on one end of the rope, the maximum force that can be sustained on the other end without the rope sliding is equal to T1 times e to the mu phi, where mu is the coefficient of friction and phi is the angle of contact between the rope and the crossbar. However, we cannot apply this capstan equation directly to the looping pendulum, and that is because here we assume that it's not sliding and that it's static. However, in the looping pendulum, there's clearly sliding motion with the heavy load accelerating at the start. Therefore, we need to make certain corrections to the capstan equation in order to be able to apply it to the looping pendulum phenomenon. We can do this through entirely re-deriving the capstan equation and introducing new terms for the acceleration into the equation. And solving this first order system with integrating factors, we can arrive at this result. Notice here that this is essentially just the same capstan equation, but with 2 additional correction factors, and that both of these factors are directly related to lambda, which we define as the linear mass density of the rope. What this tells us is that the more massive the rope is, the heavier it is, the greater the value of lambda, so the more correction is necessary. We can see this in this graph here, where with lambda values of up to 5 and 10, we can see a clear divergence between the corrected Capstan equation and the original version. However, experimentally, the lambda value we use is closer to 0.001 kilogram per meter, and there's not as much of a difference. So in the end, we can assume that this mass is negligible, that the acceleration doesn't need to be taken into account, and ultimately, that we can still rely on using this original Capstan equation. So with all the equations that we have derived so far, we can rearrange it, simplify it, and solve for h double dot and theta double dot, our original coordinates. Here we get a system of two differential equations, and notice that these are incredibly difficult to solve analytically and by hand. Therefore, we chose to use a numerical solution using Livermore's method for solving ordinary differential equations to derive numerical solutions for the variables in our system. So here you can see plots of h and r with respect to time. Here, however, there's another correction that we need to make, and that is because there's a small nuance in the application of the Capstan equation. The Capstan equation actually only describes the maximum boundary between not sliding and sliding. And the equation itself can only be applied to these two regions where the looping pendulum is in motion. However, for this case, the Capstan equation cannot be directly applied, and we need to make changes to our simulation, to our equation to account for this fact. So after we make these corrections, we get a much nicer numerical solution. Here you can see how during the first phase, when the heavy load is dropping, the h value consistently increases until it gets to this horizontal tangent. When the velocity is 0, then the heavy load stops. Then after that, it enters phase 2, where the h value is constant and the heavy load doesn't move any longer. However, you'll notice here that the r value continues to decrease slightly. This is because the light load continues to circle around the crossbar, and with each successive cycle, the radius gets shorter and shorter. We can also convert this into a computer simulation to track the trajectory of the light load. And here, if we look at the final trajectory, you'll see that it exhibits the same patterns as we described earlier. There's phase 1 where the heavy load is dropping, then there's a clear stop, and after that, there's a uniform circling around the crossbar by the light load. If we compare this to images we find online of people who have captured this experiment with long exposure cameras, you'll notice that the trajectory of the light load is very similar. And therefore, through this, we can qualitatively see that our simulation and our theory accurately predicts reality. We can derive further confirmation of this through a series of experiments that can further compare our theory and data. For our experiment, the independent parameters that we chose to examine are the heavy load mass, the initial displacement of the light load, and the release angle. And throughout this process, we control the light load mass, the crossbar radius, the string type, which could affect both friction and elasticity, and finally the crossbar material, which could affect friction. The dependent variable we chose to measure in our experiment is the angle of the light load when the heavy load stops. The reason why we chose this dependent variable is because by knowing the exact point at which the heavy load stops, it can give us more information about the conditions under which that stop was made possible. So we first padded this experimental apparatus specifically designed for the looping pendulum. There's a table stand so that we can place this on the table, there's a crossbar, and most importantly, there's this release spring. What this allows us to do is to carefully measure this initial displacement and angle for the light load so that when we conduct multiple trials, we can ensure the consistency of our initial conditions and the consistency of our results. We fabricated this using stainless steel box channels, and basically for each trial, what we did is first position the release spring into the predetermined displacement and angle. We then installed the looping pendulum, release the light load, and videotape the process, then check the video to get the measurement for the stopping angle. So now we can compare this with our theory, and we did this through generating a theory curve. Basically what we did is we ran the simulation hundreds of times, varying the parameters each time, and getting the stopping angle that is predicted by the simulation. Then we can plot this along with the data. So here you'll see this is the graph we got for our first parameter, the heavy load mass, and both the theory curve, which is the red one predicted by the simulation, and the experimental data, the blue dots, agree that as the heavy load mass increases, the stopping angle increases as well. This agrees with our initial conceptual understanding of the phenomenon, because the greater the heavy load mass is, the longer the time it takes for the centripetal force and the friction force to increase to the point where it can match the heavy load's weight. And therefore, because of this longer period of time necessary, the stopping angle is a bit larger towards this side. For our second independent variable, we look at light load displacement, and here both the theory curve and experimental data don't seem to show any correlation between these factors. To be honest, we're not entirely sure why this is the case, and we're open to any suggestions from the opponents and the reviewers. However, one guess that we have is due to the acceleration term, the centripetal acceleration term for the light load. When we release it from a larger starting angle, the value of r is greater, but at the same time, the angular acceleration is smaller, so therefore the angular velocity will also be smaller. However, we suspect that if we do this for trials where there's larger starting lengths, we'll see that the effect on the angular velocity due to the square term will begin to outpace the increase in the actual value of r. And therefore, in the future, if we do this experiment with a larger range of values, we might begin to see some different results. The third variable that we look at is the release angle. And here again, both the theory curve and experimental data agree generally that with a smaller starting angle, we get a larger stopping angle. This again agrees with our conceptual understanding, because with a smaller starting angle, meaning that we release the light load from a taller position, the light load has more time to accrue a tangential velocity, which increases the centripetal force, making it easier to stop the heavy load. However, this also leads to more error on the part because of the faster velocity, and this is why we see more error towards this side. Can you go back? One side. So in the end, we developed a conceptual understanding of the phenomenon and derived the equations of motion. We found a numerical solution, and we collected experimental data that supported our theory. And although there is some error, the sources of error are both acceptable and explainable. And ultimately, we have to see that physics is never a perfect process, so there's still work we can do in the future, including expanding the scope of our theory to cover more assumptions, or expanding our experimentation to cover more parameters. However, we feel that our explanations so far, both theoretically and experimentally, have proven to be successful. Thank you.
So firstly, we've seen in your presentation you've done a lot of numerical analysis of it, but there's some of the harmonizing, there's some difference between the factor and your simulation. So firstly, could you give us any video, like how did you conduct those experiments? Like how you really do it?
Can you go to the video slide? We don't have the exact video because we actually took this video after we finished all of our experiments, but in reality what we did is that we moved this release frame to the position that we wanted to start the light load from. We secured it, then we dropped it from there.
Okay, so then could you turn to your experimental data, so regarding the heavy load mass, light load displacement, and releasing angle. So how do you actually consider those data are actually correlating into your theoretical line? Because since they're having a great and long error bars, and they are fluctuating together. So how do you think, like, why do you think that is consistent to your theory? Because you have the previous one. So why do you think this is not a phenomenon itself? Because think that you can got the second one over there and the third one lower than it. So how do you think that with only how many experimental data I get? How do you think that it's really consistent to your theory?
Thank you for your question. And the first thing is that if we don't look at this data point over here, we'll notice that there is in fact a horizontal trend. But if we include this, in the end we have to admit that there are a lot of sources of error.
One more. Have you conducted any data analysis on the critical? Are there any critical criteria in this phenomenon?
Can you define what you mean by critical criteria?
Maybe when does the phenomenon won't happen?
Basically what we did is first we conducted a quantitative
Time's up.
analysis.
So, separation of the components.
see the execution, and then we did do it. I'm not sure it's like the same what he said.
So honorable jury and fellow commenters, today I'm going to be opposing the problem number 14, looping pendulum. So firstly, let's take a look at the problem statement. Connects two loads, one heavy and one light, as stated in the reporter's presentation. So well, according to the problem statement, we could actually derive two main focus on this related investigation. So firstly is what does the motion of the light load have actually to do with the motion of the heavy load? What are the relationship of these two motions respectively, and what are the trajectories of two loads respectively? Okay, so we'll just like further conduct the analysis of the motion. So first, let's give an overview of the reporter's presentation. So at the first part, I give an introduction of the phenomenon. Like, well, they have a clear picture, a lot of clear picture for helping us to understand what exactly is a phenomenon it is. But they have non-clear demonstration on how they do the experiment part in reality. And then secondly, in the qualitative explanation, they did not mention the elasticity or other like relevant parameters would affect the phenomenon. And also, but they had done great efforts on making correction on the theory to make the risk situation at first part. And then next experiment is the experiment part. They did not actually explain graph clearly like they had. We believe that we'll solve it later in the discussion, and did not explain the means that how you guys actually collect the data of it, and which I would be interested and curious about. And that's in the conclusion. They did not mention clearly that that's how your experimental data actually correlate to your theory and your results. Okay, so first in discussion, I would like to talk about like what we talked about previously about the light load displacement and critical criterion, the respectively situation from UK and US respectively, since I think there's an association between them during the whole motion in the rotation. And the component on the axis discussion on the possible experimental error and the effect of the total mass on the phenomenon, which I think could be it's a little bit different since you fix the amount of heavy load and change it on the light load, opposite one. Okay, so and last we could have a discussion about what kind of relevant parameters will actually affect the phenomenon. So thank you. I would like to give you the next part. So firstly, regarding the light load displacement, according to your conclusion, you say that the light load displacement are actually consistent to any other kind, right?
We're not exactly saying that. We're saying that for the length For the range of lengths of light load displacement that we looked at, we didn't find any obvious correlation. However, we feel that if we were able to conduct this experiment on a larger scale, that physically allow for us to have longer light load displacement, we might see some patterns begin to
And
emerge.
how about a smaller scale? Like, I assume that you're using the lens of around 50 centimeters, right?
Yeah.
Have you like tried like 30 or 20?
We tried the range of around 60 centimeters to 100 centimeters, but we haven't tried the shorter lengths because that didn't exhibit as much of the wrapping part as ideal. However, in the future, we could definitely try that and take that into
Okay,
consideration.
so let's talk about it along with the criterion. So first point, does the motion of the starting point, which we say as a pretty obvious change in the phases,
Yeah.
do you think the stopping points always occur in the first rotation of the light?
For all the experimental trials we've seen, yes. However, we have also observed some special cases where when it loops around, the tension force is enough to cause it to stop momentarily,
Yes.
but the continued looping reduces the tension force again, and it doesn't have enough time to completely decelerate, so therefore it continues falling and the actual stop happens on the second round.
So you actually have an observation of
We
a
have
second
that.
drop, right?
Yeah.
Also, I believe that is a very interesting phenomenon in this aspect of physics. So have you ever tried any theoretical attempts to like determine the range of what certain criterion such as the mass ratio, the length, or the initial angle that could actually potentially exhibit this kind of phenomenon?
Are you referring to the criterion under which we can see the phenomenon occurring?
I mean, like, such as, just for an example, such as while we're using the mass ratio of 1.5, of 1.10, we would actually see a very obvious, like, the stopping point at the first part, because it's accelerating very, very fast, and decelerating very dramatically, right?
Yeah.
But like, while we're choosing a very, very close ratio, such as 1.3, which is relatively small compared to all your data, so I think that it's pretty lack of the comparison while in a shorter scale, because while we're actually doing is like you're mainly focused on what's actually just normally happening in general case. I believe that there's a lot of things that we discuss about like what actually happens in that stress level. So do you guys have any description on the threshold or how you guys?
We look at the threshold qualitatively. So as I explained before, with our conceptual understanding, we're looking at the relative masses between the heavy load and the light load, and we also look at it through our simulation. So by looking at our simulation, running a simulation for different parameters, we've actually observed all of these different effects happening, where it doesn't stop at all, or the special cases that we mentioned earlier. And unfortunately, we didn't have enough time to collect quantitative data on that, but through the simulation, we have shown that our theory shows that all of these are possibilities that may occur.
Oh yeah, because the opponent thinks that the critical criterion on every variable that we use has actually could be divided into various sectoral conventions such as this first drop, second drop, third drop, and any others, and very closing to which the phenomenon will happen.
So ultimately, I would like to point out that for the looping pendulum, there's so many parameters that go into it, it'll be impossible to investigate all of them. So we prioritized the cases that we thought were most important, and that corresponded most of the problems.
Yes, I mean, of course, while discussing, you have to fix all this.
Yeah.
Yes, as well, it's very complicated. So, well, about the firstly about the component on z-axis. So it's a non-problem regarding your experimental methods. So things that in our case, we're analyzing it in a 2D case, right?
Can you explain what you mean by the z-axis?
I'm just going to be.
Okay.
So, like, while you're trying to drop the light load directly to form a rotation, so there's always a little bit awkward that it sometimes just hits the line which is hanging the high load, the heavy load. So how are you going to prevent this kind of awkward?
That was a big difficulty when we were conducting experiments. So basically what we did was that we chose light loads that were actually smaller, and we only considered the experimental data when it didn't hit the rope.
Okay,
so our data is without the hitting.
So you mean you like take it a little bit closer to the camera?
No, we released normally, but we only took the data when it didn't hit the rope.
So why do you think? So you mean that it's perhaps a little bit deviation from your releasing, so that's cause it does not heat it, right? Just like if you're directly releasing it, it's gonna heat. It's gonna hit the line,
not
right?
always, because we chose a very a physically small
angle
object for the light load.
Oh, okay.
So it didn't hit in all of the trials, and we only used the ones where it didn't hit.
Okay, so next, do you think the difference between the value of kinetic friction and static friction would affect your experiment?
Not major, because for the first part of the experiment, the phase 1 I mentioned earlier until the stopping point, it's all dependent on the coefficient of kinetic friction, and only after that do we see the coefficient for static friction coming into play. However, for this later part, we don't actually need to consider other movement anymore because there's easier ways to model it. Easier ways to model it by just looking at the spiraling of the light load. And also, we didn't believe this was very important because from the references and papers we looked at, some people actually tried to measure both of these values, and we found that they were really close.
Yes, because like while we were like saying previously on second drop, and they are potentially a critical criterion for it. So I believe that is a pretty important role in it, because since we are only in a range, as you say, we could actually observe the phenomenon.
Yeah, I agree with what you said. So basically, if we are only looking at the general case, then it's not that important. But if we're trying to extend this to special cases, then that consideration might be more important.
Okay, so could you get back to your experimental graph, because since perhaps it's about time control, you did not. I did not receive a great explanation.
Yeah, I'm sorry
on the
about
error bar. Okay. So could you give me that again? Like, why is the error bar acting like that?
Well, some of the factors that are more experimental errors that we didn't take into consideration are the actual vibration of the crossbar. For example, when sometimes the load mass hits it, the rope hits it with a stronger force, there's some vibration that might cause the heavy load to sway a little bit. However, we didn't feel like this was crucial to the actual phenomenon, so we didn't investigate this any further, and we assumed that it was negligible. However, you can see, next slide please. We mentioned earlier that at these smaller starting angles, the light load has a much higher velocity. And at these velocities, the shading can become more erratic and therefore create more error that you see here.
Just like pertaining to this graph itself. So like we've known as qualitatively, it actually forms in downward and that's a negative correlation. So do you think what is the actual difference between your experimental because what's the difference that caused this curve to work like this instead of this red curve?
One possibility is next slide please. The drag force that we didn't take into consideration in our theory. At first we assumed that it was negligible due to its small scale compared to the actual weight of the masses. But however, we feel that because at these angles the velocity might be higher, this drag force could be greater, contributing to more error. So in the future, we're going to refine this theory.
So really, that's a clarification. How do you define your stopping? How do you define your stopping angle and starting angle?
Can you go back to the degrees of freedom slide? Here defined with data.
So this one is your in this direction is your starting angle and your stopping angle.
Yeah, basically the angle of contact between the rope and the crossbar.
So I'm just like a little bit curious about it. Why are you showing the correlation between starting angle and stopping angle instead of the difference between stopping angle and starting angle to starting angles?
This is because the phenomenon doesn't actually depend on the difference. For example, if we release it from here and it ends up here, there's a clear difference between releasing it from here and it ending up here. Because for this range, the gravitational effects are different at every point. So therefore, the exact starting angle does play a role, and it's not just the difference.
Okay, and then just a few more regarding the some discussion about the variables. So do you think that because as in your presentation you fix the weight of the light load, right? You fix the weight of the light load.
Yeah, we got that concept.
So what do you think is the difference between just simply changing the mass ratio?
We didn't actually, based on the theory, we don't actually see the mass ratio as that crucial of a component. However, we do feel that there's a relationship between the two masses that is a bit more complex. So the effects of increasing the heavy load would be tantamount to the effects of decreasing the light load, and vice versa.
Okay, just for another hypothetical question, what do you think the total mass, in in my previous question, like well fixed ratio between the mass between the two loads.
Yeah.
What do you think? What would happen if we change the total mass of the two loads?
If we increase the total mass of both loads, because both sides will be pulling down with a greater force, we might see a greater friction force that exists in the system, and therefore the heavy load might fall a bit, might decelerate a bit faster.
Okay, so now that's part regarding the parameters. Do you think how would the radius of the rod would affect your experiment?
Mainly because in all the cases that we've observed, the heavy load swallowing the light load is still in its first rotation. The radius doesn't play that much of an effect. However, this is more crucial for the later spiraling phase because this determines how fast the radius of rotation for the light
Okay,
load.
so the last part. What do you think the elasticity and reality of the rope would affect your phenomenon or your experiment data?
We've actually done some experimentation with different ropes and different weights. And we found that there's actually a very narrow boundary between when a rope is rigid and when it just snaps. So in reality, we don't feel that there's that much elongation that happens with the rope.
End of
Instead-
discussion.
Okay.
Opponent summarize the discussion.
So throughout the presentation, we've seen that the reporter gives us a clear idea on explaining what happens actually in the phenomenon and gives us a lot mass of their numerical simulation. But actually, we think a great improvement for their presentation is that could include like some more experimental data and more explanation on doing those different parameters physically. But instead of just using numerical situation, and will be more convincible to both any other guys listen to the presentation. And throughout the discussions, we talk about that the So we've talked about like how would the relevant parameters would affect, such as the radius of the rod and the elasticity of a rope, and how would like the critical criterions would actually act in this phenomenon, and how would and make some clarification on how they actually did the
Time's up.
experiment. Okay, thank you.
Reviewer, please ask question.
Okay, hi, I'm the reviewer team. I have some questions to ask as a report. Since you made the simulation using your equation of motion, so can you ask us how you measure nu as and use k, the static friction and kinetic friction?
You can go to the appendix. Yeah, this slide shows how we can measure mu s by having one known load over here and slowly increasing the
Okay, I
load.
understand it. How did you measure mu k?
Mu k we found was a bit more difficult to measure, and we read from papers that it's very similar to mu s. So what we ended up doing was instead using a fitting method
Also,
to
you
fit
didn't
the.
measure yourself. You just read the reference and put it in.
We haven't found a consistent method for measuring mu k, and if the review has any suggestions, we will definitely welcome it for the future.
Okay, thank you. So you mentioned there might be collision of the string, and then you said you just discard the data. Did you consider to investigate why that happened?
The collision of the string is mainly because when the light load is dropped at certain angles that are not very controllable in the experimentation, it forms a just right trajectory to hit the rope. However, this is not part of the phenomenon at all. This is just.
So you simply just discarded when you had this.
This is basically just garbage data, so we didn't need to include it.
Okay, thank you. So can I ask the opponent, like how might the collision of the string be reduced?
Well, like there are several parts, but actually the best way to do it is give a slightly different from your drawings, and which will actually reduce the deviation while you're trying to calculate the rotation, the length of the string coil. Because since if you are going to do it in a larger angle, it's certainly going to give a change on how tight you keep the length of the coil.
Okay, thank you. You also asked about the total weight, which might be the result. How do you think the total weight would be?
To the weight, I think it's not theoretically would be very, very prominent to this phenomenon, but I think it will be reducing that. It will be more easier for us to reduce the frictions. I mean the air resistance inside the system.
Okay, thank you. Can I ask the reporter that you mentioned that there's actually another occasion where it's switched here and then go back. So can you can you explain what differs the two?
One is that when the light load swings up, the tension force is enough that even as it continues swinging this way and the tension force decreases, the heavy load is still held in place. but with certain parameters, when the tension force decreases as it swings back this direction above the crossbar, that isn't enough to hold a heavy load, and we see the stopping happen on the second or third.
Okay, thank you. How about your component? The fact that there's two phenomena that might happen. One is that it will swing back, so what
I think it would be great if we did discuss on the critical criteria, because it's certainly a range for it.
Okay, thank you.
Preparation of the reward.
Very good, switch to
Reviewer, please take some floor.
Okay, hi, I'm a reviewer today, and I'm the reviewer of the 14 of the pendulum. The common statement says that you connect one light bulb over with a shape over a rod. The light bulb will slip around, which will prevent the heavy rod from falling. And then this is a first outline. I believe that the Ford did well on elaborating on their theory, and also he has sufficient parameters. However, I believe that the video is not really clear, and she mentioned about releasing methods. However, I believe that he didn't really show how they release it. And then, although they did have sufficient parameters, I think they have lacks of experience. Since this experiment is not hard to do, and they only have 5 or 6 cells for each experiment. And then, I think the error bar are too big, some of them, and it doesn't really match the theory. And then for opponents' pros and cons, I think what they did well is that they discussed the displacements of the light bulb. And then also they discussed about the other phases of the phenomenon, which the report didn't discuss. However, they didn't discuss the initial velocity about how they use the reducing device, and then they didn't compare the result, and they didn't further discuss the phase of the phenomenon, which I think is quite important. On this discussion, the opponent asked about the second drop, and then the opponent said that it occurs because of the friction cannot hold the rod, and I agree with the opponent, and I also think that they should investigate on that. And then the opponent asked about there are other phases for this phenomenon, and then the opponent said that they did observe many phases, and then due to lack of time, they didn't further investigate. However, I think there is many phases. There is many phases, but the course should investigate and explain it in their theory to make it more complete. Next, the opponent asked about collisions during the experiment, and the course said that they only collect the data that didn't collide, which means they discard the other data. I think they should do further investigation of the collide conditions. And then the next discussion of the opponent is they asked about the error bars. And as I can see, the error bars is quite big for some of them. And the first answer that it is because of the drag force. But I believe that the drag force is not really that big. The drag force is not that big factor that will influence the error bar. So because I think the ball is heavy enough and the drag force should be negligible. So I think the port should make sure what makes the error bar that big. And then they also discuss about the fixed ratio and increase the total mass. And the port answered that the friction will increase because if you increase the total mass, and I agree with the report. And here are some point lists. As I have mentioned, the report only investigated on maybe the successful one they mentioned. But I think they should also investigate other cases of this phenomenon because it does occur when you are doing experiments. And then the report should also do more experiments instead of using only simulation. And plus, their simulation for they use the new K they use for simulation is took from the reference. So I think they should do more experiments. And then the report is like a connection between the theory and experience, which the opponent team did point out. And then for the opponent team, oh my god. Okay, and then for the opponent team, they did discuss the measurement of the friction coefficient. As I just said, the report did use simulation, and then they did need static friction and kinetic friction. They did measure static friction, however, they didn't measure kinetic friction, and they said it's from the reference. So I think this is what the opponent team needs to point out. And then, as I have mentioned, the opponent team didn't further discuss the different phrase because I believe that there's more phrase than just the successful one. So I think she should discuss like what causes it to differ from those different phases. Thank you.
Reporter, please make conclusion.
Thank you. We're very grateful for the attention and review of our theory by both the opponent and the reviewer, and we definitely don't believe our ideas are the only correct ones out there. However, the main point of contention between the opponent and the reporter is in the lack of experimental data. While we agree that there's always having more data can improve our presentation, this is an endless process, and for the data we have, we can already clearly and appropriately justify our theory. And furthermore, we achieved consensus on many topics, including the effect of the masses and on experimental errors such as drag force. And I agree about the opponent's suggested technique of using larger masses to diminish the effect of the drag force. However, the reviewer pointed out that the drag force isn't a suitable source of error, and I agree that the drag force is only prominent under some cases where the masses are smaller. However, I'll only mention drag force as an example, whereas there are other sources of error that exist in the system, including friction between the ropes that we didn't take into consideration in our theory. So ultimately, there's lots of different sources of error that made this extremely difficult to match experimentally, and that's why we see some of the larger error bars with some of the faster velocities. However, we feel that this is understandable, and in the future, should we have more time to improve our theory, we could definitely take all of these into consideration. Finally, the reviewer brought up the point of collision, and we completely disagree with that because we feel that collision is just garbage data. It's tantamount to accidentally dropping a mass or something like that. It doesn't have any bearing or relevance to the phenomenon at all. And we believe that both the reporter's suggested technique of releasing at a slight angle and our technique of discarding these garbage data are already good ways to deal with the potential factor of collision. So ultimately, we thank everyone for the fruitful debate, and yeah, thank you.
Okay, it's time for jury to ask questions. Any questions? Yeah.
Hey, I've got a question for the reporter. Can you show me I think the last slide was showing the friction of the coefficient of friction. Yes,
how
this one. What's this mu is? The mu is the static friction?
This is for static friction.
Is that right? If you change the mass ratio, you change the static friction? Is that mean? Is what you mean?
What this means is that M2 is the maximum mass that can be held on this side. So what this basically tells us is that if we can find the maximum mass that can be held on this side, we can determine how much friction there is occurring between the two surfaces. This is coming from the direct results of the capstan equation.
So for example, if the mass ratio is the heavy one is 2 times the M1, is that the mu s is pi log 2 over pi? Is what you mean?
Yes, it is. But M2 is the maximum mass on this side, not any mass that we choose. Is that clear? Like for each surface,
So all that means is the steady friction is just mostly just it's constant. The maximum, okay.
yeah, it's,
Coefficient.
The coefficient.
the coefficient is constant for the same two surfaces. But as we increase this mass one, for example, the maximum mass that can be held on this side will also increase with it. So that's why you see this relation over here.
I got a question for you. You had a result of the starting angle versus the initial length,
Yes.
and you plotted as a flat one, the red curve. Is that the previous one? Yeah, this one. And my question is that reasonable to have this flat theoretical result? And the second one is how it's going to extend. I mean, if you use 2 meters instead, it's going to be all the way flat or what?
Let me clarify. This curve is a regression line. This is the result from our simulation. And
That's right. Well, that was my question.
Yeah.
Is that reasonable?
This is one of our questions that we proposed at the start, and we think that based on our understanding of centrifugal acceleration, that might provide an explanation of why this is constant, at least for this starting length. However, we feel that if we increase this, there might be more changes up and down.
In what sense? It's going to be higher or lower or
If we increase the starting length, this might outpace the increase in this. So the centrifugal acceleration overall will be smaller, and therefore we might expect the stopping angle to become larger.
So you are able to extend it up to 100 meters?
Given the given the ability to conduct an experiment at that scale, we might.
I have actually 2 questions. But first question is for both teams. So could you give us a clear explanation of the phenomena in 3 sentences and without any force analysis? So what kind of mechanism lead to this kind of looping phenomenon?
Because when you release it right now, it will slip around the rod, and then there will be static friction that stops the heavy load from the body.
Well, I believe if we actually seen it in the energy aspect, those things that is pretty great. They were trying to transfer the potential energy from the light load to the heavy load to the starting point.
When the light load swings down, the momentum pulling outwards, plus the friction force between the rope and the crossbar contribute to the stopping of the.
But what I mentioned is that without force analysis, or more, let me put a question more clearly. So, what kind of is there any what kind of competing mechanism leads to the light load to rotate around the horizontal bars?
Can you clarify what you mean by competing mechanisms?
Just competing mechanism.
There's friction and there's momentum.
Can you rephrase the question?
Rephrase the question. So, let me. So, why? No, then I will give you the answer. So, I cannot rephrase it. Sorry.
Can you repeat the question?
So, the question is, can you give us? Can you tell us with what kind of competing mechanism make the light load object to rotate around the horizontal axis, the horizontal bar?
The system trying to acquire compensation in energy aspect, I think.
So
Can I ask one more?
sure.
So I want to simple one. So if you take the ratio for the light load to the heavy load, okay, can you see is there any critical ratio to see this phenomenon?
From some sources we looked at, that ratio is important, but we don't feel that the ratio is as important. This is because we had a modification to our capsule equation and we applied it a bit more carefully than we saw in some
Is there
references.
any ratio you can see this happen?
Can you clarify what you mean by it?
Okay, the light to, the ratio between the light load and heavy load.
Yeah.
If it's one, that is equal mass.
Yeah.
Okay, so it's 0.1 versus 1 is 0.1 is 1 is another 10 times. Okay, so all, for example, for these two, you can see this happen.
Like 1 to 100.
Yeah,
Oh,
It's gonna happen. I mean,
is this
it's
happen?
1 to 100.
Always happen?
no, it doesn't always happen. There's certain thresholds at which, for example, the heavy mass becomes too heavy for the lateral to be able to stop it.
So, in your experiment or in your theory, can you give me some critical value for this?
We've observed this in both the simulation and our experiments, but I don't have the number on the top of my head.
How about Conan?
I believe there's certainly such a value associated
Do you have
with
any
it.
ideas? Is it 110 or 100?
I believe there's certainly an association between the real material of the balustrade and the iron rod. But I'm sure that certainly there is a value for it.
Can I add one thing?
I think the mass ratio that does influence, and I believe that it also you also have to consider maybe the length of the string and the angle that you release it, and
Fixed
also the
angle.
friction.
Fixed angle. The angle is fixed.
So you also have to control the consider the friction of the rod.
Well, everything is just fixed. I only ask one parameter, the ratio.
The ratio.
Okay.
If you one or two testing, you can. Okay, what do you want to say?
We don't feel that there's actually a fixed number specifically because it really depends on the other parameters. So there's not a specific number that's universal amongst all cases.
Okay, thanks everyone. So it's time for the jury to score.
Differs for the prevalence of the parameters. Like, yeah, but that's what and then Sam just said that it was an exercise that is she didn't understand that. No, just you have to say that this M is max. Yeah, that's what I have to say. Mu S is constant for everything. We use mu S to determine M max. Yeah, that's not using M max. That's all M max. Well, you should say use it the other way to understand. That's what I said. I said use the maximum. If you use the other way, you can also you have to make it right.
So the score for the order. 77574.
No, later.
The score for the opponent. 88785. The score for the reviewer. 77785.
Thank you.
So, Professor Guo, you want to make a comment?
First, for the reporter, so although you did quite some simulations and also do some theoretical analysis, but you didn't tell us what the physics is actually about. For example, for the correction of the friction, what kind of physics you input. And secondly, in your simulation results, So you didn't mention any parameters that you put in, and we don't know the results of the if the results from the parameters are they physical. So basically, so we don't know the physics. Okay? And also during the discussion, you say too many empty words. For example, too many parameters to do, and we can choose. This is for all the TYPT problems. There are always a lot of parameters to do. So basically, what your response is basically superficial, that you didn't tell us anything about that physics. So therefore, your grades are low in this regard. And also for the opponent, you have made one very big mistake is during the discussion is that you mentioned that you using some mass ratio and observe some very, how do you put it, so significant difference, and which you cannot do. Because in this case, even this sentence, you simply mention your work. You can input your thoughts, but you cannot mention it. For example, later on you suggest some hypothetical questions. That is good, but that is a very big mistake. Also, as I mentioned, if the reporter has so many physics you cannot explain, then and then during discussion you didn't discuss into details, or also try to finish all your questions, but not touch into the physics. Therefore, you got I think your it just have some average performance. And okay, so again, this is again also the same for the reviewer, since both sides are just doing this kind of they just didn't mention so many physics, and you should point it out. Okay, and point out so therefore it's also some average performance.
Thank you.
Okay, thanks to everyone, and we have finished on this stage. So let's come back in 15 minutes. The opponent challenged the opponent for the problem number 1. Right? Yeah, number 1. Okay. So all teams, please write out their representatives. Here is a preparation of the reporter. Presentation of the recorder.
So, good afternoon everyone. I'm from TYPT and I'm here to report topic 1, investor staff. So this is our outline. First we'll introduce what is a corona motor, and then we'll introduce the observation we get, and then we'll tell you how we construct a corona motor, and then the theory to predict the phenomenon, and next the experiment, and next the conclusion. So first introduction. So this is our problem statement, and from this, build a simple motor whose propulsion is based on coronal discharge, investigate how the rotor's motion depends on relevant parameters, and optimize your design for maximum speed at a fixed input voltage. So we can grab 2 key points from here. 1, what parameters will have an influence on coronal motor's rotation speed? And second, how to optimize the system. So this is a coronal motor we searched from the internet. So coronal motor is an electrostatic motor consisting of electrodes, and which is over here, and surrounding an electric insulating cylinder, which is inside, with conductive inner lining to attract electrons. And so the voltage applied to the edges of electrode and create intense fields. And these intense fields will ionize the L molecules and cause a corona, and further to charging surface of cylinder. And from the charge, we can use this charge to cause a repulsive and attractive pulling force between electrodes and cylinder. And finally, we can let the cylinder to rotate. Next, the construction of the corona motor. So basically, the corona motor consists of 4 parts. And first, this is the high voltage power supply, and this is the cylinders we use, which is made of plastic top. And there's a model here. And under it, we use the paper to stabilize it. And inside with aluminum foil as an inner conductor. And next, this supporting wooden board to place the cylinder. And next, the electrode, which is made of aluminum board. Okay, so this is how we put it together. So right hand side is the top view, and left hand side is the side view. And so here you can clearly see that the conductive material should be inside. And there's one thing to be mentioned, that one electrode should connect to negative and one to positive. So this is the design of the rotor, and we have three kinds of height, and the foil plays inside the cylinder, and the shiny side of the foil facing outwards, and the number of foil P1, and the distance between the foil and the outer layer of the cylinder will be one layer of plastic cup. And next, the design of the electrodes. So the size would be 4 kinds, and the number would be 2, and the arrangement will be AB or AC. We'll talk about the arrangement later. And next, the angle between electrodes and cylinder is 0 degrees to 7 degrees. The angle we talked about here is this place, the red part. And next, as for the electrode has no sharp edges over here, which is flat here, and it's covered insulation layer, which is the green tape we use to insulate. And the distance between electrodes and edge of cylinder will be 0.15 centimeter. And this is a definition of the AB arrangement. So first here you can see is the AB arrangement, and the AB arrangement will cause a clockwise rotation, and next the AC arrangement, and we classify AC arrangement to two kinds. One is forward connected, which can cause also a clockwise rotation, and next the backward connected will cause a anti-clockwise rotation. So this is the observation video. So right hand side is the top view and left hand side is the side view. We can clearly see that there are sparkles here, and which is the corona discharge. Okay, theory. Okay, so first we're going to talk about what mechanism causes the cylinder to rotate. So let's first focus on this part. With zoom in, we can see that there are 3 electrodes, and first start from this negative electrode. Okay, so the negative electrode is connected to a high voltage that can apply the edges of the electrode to create an intense field. So there is an intense field, and the intense field causes the conductive lining inside, which is the aluminum foil, to gain a positive charge, and the positive charge will attract those ionized air molecules to stick, the electrons to stick on the insulating cylinder. And because the negative will repel negative, so the electrons will be repelled and start to move away from it. And since that the electrons is on an insulating cylinder, which means that when the electrons want to move from A to B, it should have to hold the cylinder to rotate with him. So the cylinder began to spin. And when the electrons get clear next to the positive electrode, there will also be an intense field and cause the inner lining to gain a negative charge, and the electrons here will be absorbed by the positive electrode and cause the insulating cylinder to gain a positive charge. And similarly with the negative electrode, it will be repelled again and attracted by the negative electrode, and so go on the cylinder begins to spin. So next, the angle of electron to create torque. So the red line is a prolonged line of electrode, and this is the electrode that with insulation. And since that the electrode is insulated, so that means the electrons can only spread out from this circular, certain angular, and we call this angle theta A. And besides, when the fixed voltage is applied, the maximum travel distance of an electron R is fixed. So we can draw a circle like this with R. So the maximum range will intersect the cylinder in 2 points, these two. And between these two, this is the maximum angle electrons can reach the cylinder. And when we overlap theta A and theta B, we can get a theta C, which is these electrons is the only electrons that can create torque. So from this, we can calculate the repulsive force from the electrode, and due to the force, we can calculate how many torque we gain, and finally we can get the rotation speed from this. And next experiment. So we studied here we studied three kinds of parameters. First is the angle, and we classify these parameters into two types, which is one that the electrode with insulation layer, and one with no. And let's first start from the one with no insulation. So we can see that 0 degree and 75 degree is the lowest, and the 45 degree is the highest. That's because majority of the electron does not move along the prolonged line of the electrons, and attracted by cylinder turns direction. And when the electrons are nearest to the cylinder, which is 0 degree and 75 degree, the maximum direction change. And so this is an observation video. We can see that the sparkles not only appear in the edges, it also appears in of the electrode side. And next that we study with insulation layer. And with insulation layer we can see that the rotation speed is positively correlated to angle. And that's because insulation prevents electrons from going sideways, and the force that pushes the cylinder is more concentrated. So as angle increases, the torque created increases, and rotation speed increases. So here you can see that the sparkles only appear from the edges, not from the side. So let's take a comparison between these two, and we can get that highest rotation speed of O is under no insulation and at 45 degrees. And the total amount of electrons generating the torque will be lower than with insulation. And even though lots of electrons are going sideways, we still generate torque. So next parameter to talk about is the arrangement, and we can see that AC arrangement with the forward one is better than O, and even better than arrangement AB because the angle allows both electrodes to do positive work. Here we can see that AB arrangement here, the positive one, because it attracts the electrons, so it will give a negative work to let the cylinder wants to stop. And next, because we changed B to C, so both of them here will do positive work due to the line we draw here. And when we change both negative and positive, we can see that the C will do the positive work, and the C will do the positive work, and the A will do the negative work, and the reason is okay. So next we talked about the height of the foil and electrodes, which we get that both higher foil and both higher electrodes can get larger torques, so that the rotation will be bigger. And finally, the conclusion. So the conclusion here is that some of the electrons will go sideways if no insulation, but if those electrons are able to do positive work on the cylinder, rotation speed will be higher. And next, insulation prevents electrons from going sideways, so angle is positively correlated to rotation speed. And when both electrodes can do positive work, arrangement AC forward connected, rotation speed will be higher. The height of foil and electrode is positively correlated to rotation speed. And that is the group with the highest rotation speed of all is the electrodes with no insulation at 45 degrees. Okay, so that is my report. Thank you.
Okay, so good afternoon. So can you briefly explain about your optimization? Since from the statement mentioned you have to optimize your design. So it is the experiment that you do is also your optimization.
Okay, so we do the optimization from figure out under each parameter is what we
So both your experiment is your optimization.
Yes.
Okay, thank you. So can you go to your page 5?
Page 5.
Page 5.
Yes.
Thank you. So I mentioned that there should be a conductive inner landing. So you are using the aluminum foil as the conductor.
Yes.
Okay. So and also and also you are using the plastic bottle as the illusional layer. There's no illusional layer, right?
No, there's no additional layer. We only use the cups as one layer.
Okay. And about your page 10.
Page 10.
Yeah, so you mentioned that you are using the shining side facing outwards. So can you explain about the shining side and the
Okay, so there, the aluminum foil has one side is the shining side and another is the dark side.
Yes.
And we put the shining side outward so that when we see the cup, we can only see the shining side.
So what is the difference between the shining side and the dark side?
Okay, so there are 33. Okay, so we discovered that the shining side outwards would be faster than the dark side. Sure. Like this. So the shining side would be faster.
Okay, thank you.
Operation of the opponent. The opponent takes the floor.
Honorable judges, following the barriers, good afternoon. I'm the opponent from Technical South, and now I'm going to oppose from the number 1, inventor South. So this is a important statement. The simple motor whose propulsion is based on corona discharge. Investigate how the rotor's motion depends on relevant parameters, and optimize your design for maximum speed at a fixed input voltage. So this is my structure also in a problem. First, I will explain. First is how do the corona discharge propel the motion, since the problem statement have mentioned that the propulsion of the motor has to be based on corona discharge. And second is how does the rotor's motion depends on relevant parameters, and how to optimize for maximum C at the fixed input voltage. So here's the strong and the weak points of the reporter. So first he showed a very clear picture and a very clear video of the how to build up the motor and the rotation of the motor. And he elaborates on the construction and elaborate on the mechanism of the motor. And also he explained how does the phenomenon happen. And but he didn't but he stuck out formula that can calculated the angular velocity of the motor, and also he stuck out parameters like he only, and also he stuck out optimization since he didn't mention that his experience also his optimization, and also he didn't connect his experience between he didn't connect his result with the theory. So this is my points of the discussion. So first is the propulsion of the motor. So I wonder what is the main reason that causes the corona discharge to form, since as the reporter didn't mention in his report, and also how does the negative discharge and positive discharge goes, and also that in the experiment that in the video it shows that I can see that the motor was actually rotated in the constant speed, but since that he didn't calculate the friction and the air resistance in his report, so I think that also if he didn't calculate it, the rotor will be faster and faster. So but when it maintain the constant speed, I think they should I think they should calculate the friction in this, and also that the motor of the report was spinning vertically, so I wonder if maybe spinning horizontally will reduce the friction of it. And also effect of the parameters about the height of the aluminum field, and also the arrangement that he didn't really actually explain that what causes it to rotate faster, and also that he did that maybe changing the arrangement and the tilting angle at the same time will affect the motor's role. And I would like to skip to the next phase. So first, can you briefly explain what causes the corona discharge to happen?
Okay, so the corona discharge basically is because of the intense field that come from the high voltage, the electrode gain.
So it is a high voltage that causes.
And high voltage causes the high intense field, and the high intense field will cause the air molecules to ionize. And that is called a corona discharge.
Also, I actually agree with the reporter that when the voltage is high enough, this will cause a stronger electric field, and this will cause the negative electron to emit a negative charge onto the rotor surface. And can you go to your the pages talking about your AC
arrangement? And
yes. Yeah, so can you explain the two differences? So you connected the C with different.
Yeah, different positive or negative will switch.
So they switch the size. So did both the AC arrangement will causes the high angular velocity of this?
No, because when we do the backward one, it's much lower than the AC and the AB one, because we know the positive node can do work, but the work is much smaller than the negative one can do. And since the AC backward one is C to cause the positive electrode to cause the positive work, and since that the positive work it cause is much lower, so we get a lower.
So that's the direction of the rotation rotated was the same to the tilting angle that it points to.
Yes.
So if the AC look like this, won't this direction cause the negative effect to the rotors?
You mean no, because yes because but
you mentioned that one of the AC is higher than the others. And since the AC is look like this.
Okay, so I want to explain that the question. So you mean yes, sure, the C would also cause negative work, but apparently the positive work because is much larger than the negative work, and that is because of the.
So did you connect your negative node with the positive node with the same DC power supply?
Yes.
So why would the negative cause the bigger effect compared to the positive one?
Because current discharge is basically that come from the actually I said the negative node. So okay, so actually we didn't know that, but we only.
Okay, thank you. So I think the reporter should really know what will cause it the effect to the motor instead of just showing the result and didn't discuss it about the main reason. And about, so can you turn back to page 35? So you have mentioned, yes. So the shiny side, you said that is more conductive and more sensitive. So how is this more conductive and more sensitive? What causes it to be more conductive and more sensitive?
Okay, so we measure the shiny side and the dura sides.
Yeah, this is your result. So do you have your?
We measure the resistance of the current.
So you measure the current. Also, so you mean that dark side will causes the resistance of the current.
Lower current.
So it will be less conductive and more.
Yes.
Oh, okay. So I agree with the reporter that the darker side will cause the current to be will cause it more resistant for the current to go. So it will be less conductive and the angular velocity will be lower. So I think that maybe he should explain more on his reports. And also you didn't consider the friction in your experiment side. So because your power supply is keep on supply power to the rotor. So if you didn't consider friction, that it will actually go faster and faster. But this actually didn't happen. So can you explain this?
Okay, so of course there is a resistance, but we try to make the resistance to become lower. And
yeah, so
how we do that is first we use a needle to go through this, and because the needle's point is very small, the area is very small, so when you contact together, the friction can actually be neglected. And since that, yes, maybe theoretically it should be faster, but since the resistance and the air drag is won't be.
Okay, so I agree with the reporter since that he have optimized the design for reducing the friction, but I still think that reporter maybe can manufacture the friction coefficient or the damping coefficient of the angular velocity so that it could calculate the angular velocity better. And about that, you have changed your actually you have changed many parameters. So what will affect that? Maybe you changing the tilting angle of the arrangement at the same time. Like yes.
You mean the angle
yes.
between the cylinder and the electrode?
Yes.
Okay. So
like for example, that you are using the AC arrangement and you change the tilting angle, that what will happen?
Okay, so ideally, when we get the insulation layer to 75 degrees and bigger aluminum foil and the electrode, ideally we can get the best data.
Yeah. So what is so according to your experiment, then what is the best optimization?
Okay, so because as the opponent just said, both many parameters may influence on each other. So what we try to do is to find under each parameters what best condition we can get, and we take that condition as a standard and fit that into the final arrangement or the setup.
So does this causes the maximum speed, or it doesn't?
Yes, it does. But we didn't put it on here.
Okay, that's okay. So And about can you go to your page 11? That you have actually mentioned that there is no sharp edge. So since the concept didn't mention that you have to have the sharp edge, so why do you mention that there should be no sharp edge? What will happen if there is a sharp edge?
Okay, so since that the current discharge is due to the sharp the surface is, so when we get more so when we get more sharps on it, it will cause more electrons to spread out from the electrode, so the speed will be faster.
So why didn't you sharpen the edges for optimization?
Because actually the sharp edges is not so stable.
So this only because of the loss
Yes.
stable. Also, I think that yes, I agree with the reporter that when you sharp the edge, this is what causes the corona is much easier to happen. But since he mentioned that this will be a optimization, I think that maybe he could do the experiment about with no sharpened edge and with sharpened edge. And about that the pages I will see that maybe 36. Yes, here, thank you. So actually you increase the number of the electrode and the angular velocity getting slower, so what causes this to happen?
Okay, so the high voltage supplier we use here is really high, that even though two electrodes, the distance between these two electrodes are this far, it will still make the electrons to jump from here to here.
Okay,
And since that we put 4 electrons here, so the distance between them will be more closer, and even to make the electrons, some of the electrons to jump
So
to the next.
if you increase the gap between the two electrodes, will this causes the angular velocity will getting higher?
So if the rotor is bigger or the voltage of our suppliers is lower, yes, we can.
So you cannot control the voltage of your power supply?
Yes, we can.
Okay.
But the lowest we can get to is still very high.
So do you think that this is the other optimization?
Sorry?
That this maybe will be another optimization of your design?
Sure, thank you for that advice.
And about so I agree with the reporter that they actually will be the corona discharge happening between the electrode and the electrode. So and I also agree that maybe increasing the gap, this will causes the increase the gap and this will causes the corona discharge happen between the electrode and capacitor, and this will causes the maybe the energy loss will be smaller, that will causes the angular velocity getting higher. And thank you, and I would like to make my summary. And during the 10 minutes discussion with the reporter that we discussed how does the corona discharge happen, that which is when the voltage is high enough for the electric field, and the electric field will form, and the higher the electric field will be, and this will cause the electron will emit the negative charge onto the rotor surface, which causes the motor to rotate. And also the direction to rotate, since the reporter agreed that the direction of the rotors will equal to the tilting angle. And what causes the shining side to be more conductive is because of the dark sides will resist the currents of the resist the current to go. So this will make the angular velocity will get smaller. And also the friction will causes the rotor to have no accelerating, that this will causes the constant angular velocity of it, and also the change the tilting angle and change the arrangement at the same time will be another optimization, that since the reporter agreed that this will affect it with each other. Okay, thank you.
Okay, first I would like to ask the reporter, did you control how close the electrodes are to the motor?
Yes, that is the 0.15 centimeter.
And did you ever try to change this parameter to see whether the motor would spin faster or slower?
Yes, we did that. If we get too far, it will even not to spin, but if we get too close, that the electrode and cylinder is likely to contact, do not spin.
So do you have whether like data or a graph that shows whether if you move it further from the motor, will it spin slower or faster? And if you move closer, will it spin faster or slower?
Sorry, didn't. But yes, sorry.
You do, but is it?
We didn't.
We did not. Okay, thank you. Next one. Did you control for humidity of the air? Like because we know that in Taiwan, when there are rainy days, it's very humid. Did you control for humidity? Because I think that is an important parameter that could change how fast the motor spins.
Okay, so we do every experiment at a sunny day, not the rainy day, and we do it in the winter, not the summer, which we can have a lower humidity.
I understand. Thank you. And how did you determine the optimum parameters for the motor?
How we determine it?
Yes.
So we control most of the we change one parameters and see under 5 parameters we can get the highest rotation speed, and we put these parameters, the best conditions together.
Thank you. But did you graph them on a line to see which one is the maximum or has the maximum performance or no?
In this slide, no.
Okay, thank you. Okay. So as you know, the corona discharge is coming from the ionization of the air molecules, right? And so this is a question for both of you. Do you think that this phenomenon can still happen inside a vacuum?
It's a vacuum.
Where there's no air.
That's the ionized of the air is one reason of this, but a corona discharge, there will be another corona discharge that the negative electron just emits the negative charge onto the rotor surface. So I think this phenomenon will still happen.
Yes. I agree with the opponent, and since there is no air, so the electrons jump to the center directly and even cause the faster rotation speed.
So you think that it will have a faster rotation speed?
Yes.
If there's no air? Yes. Okay, thank you. And I will end my question session.
Okay. Preparation of the review. The reviewer takes the floor.
Okay, so I'm Jason, and today I'll be reviewing the discussion between the opponent and the reporter for invent yourself, question number one. So the problem statement reads that build a simple motor whose propulsion is based on corona discharge, and investigate how the motor's motion depends on relevant parameters and optimize the motor. So reporter's main points include mainly experimental ones, and he talks about how the angles between the electrodes and the motor, slash cup affect the spinning of the motor. And also, when you have a higher height of tin foil, there's more surface area for the electrodes to actually jump to, so that it will spin faster. And also the problem of AC versus DC. And when you have AC, the reporter stated that there will be less power generated from the positive electrode. So on the reporter's performance, I think some clear pros that the reporter had were a clear explanation of the phenomenon and how it affects the motor, and very successful experiments considering that we are in Taiwan and that humidity has great bearing on the spinning of the motor. And also you control many parameters, including the insulators on the side of the electrodes to stop leakage onto the motor. Some cons, I think that the graphs they have are bar graphs instead of scatter plots, and they are also without error bar. And I think that for optimization, they consider too few factors, including environmental factors like humidity. And they also have no quantitative explanation as to why these parameters affect the optimization. And furthermore, they have no theoretical backing on their qualitative explanations or theory lines to fit their data in their graphs. And the opponent's performance, some pros they had were they had suggested feedback on the improvements of the reporter's experiment. And some things I think they could improve on were that they did not ask the parameters about their lack of parameters tested or some improvements to their experiments. And I'll go over the discussion now. So in the first point, the opponent asked the reporter what causes the phenomenon, and the reporter explains that it's from the ionization of the air and from the higher energy of the electrons. I agree, and I would like to add that the corona discharge phenomenon also has the purple light, which is from the dropping of the excited electrons from a higher state to a ground state. In discussion point 2, the opponent asked, why does the negative node of the AC have a larger effect on the spin of the motor? And the reporter did not give a clear answer. I hypothesized that there's a repulsive force on the negative nodes due to the constant voltage from their voltage source. However, on the actual motor, there's a lot of there's not a constant voltage source on the motor that transfers from the motor to the positive electrodes, and there would not be a constant repulsive force there. And for point 3, the opponent asked, what causes the shiny side to be more conductive? And the reporter said that the measured resistance and the current on both sides and the darker side have more resistance. I agree with the reporter that due to the different materials there be different resistance. And some missed points, I think, are the environmental conditions. In our own experiment, the actual day-to-day changes due to humidity were a very big factor in this experiment. And also, whether or not the presence of air has any bearing on the phenomenon or the spinning of the motor. Because the phenomenon is on the basis that the electrons will excite the electrons in the actual air, and I think that the reporter had a good response that it will spin faster if it's in a vacuum.
The reporter now makes a conclusion.
Okay, so thanks to both sides, the opponent and reviewer gave the very good advice to me and to advise how to optimize the whole system, and very grateful for this. And since the corona discharge is basically powered by the electrode pulse, while the air near the cylinder and the electrode is ionized by the high voltage. And second, the related parameters act differently on the RPS efficiency of the setup, such as the amount of electrodes, the material of the surface, which is shiny or dull, and third, the position and the angle of electrodes against the cylinder. And next, the fluence, such as the humidity and the properties of the air, should be considered in order to optimize the phenomenon. And thank you to the reviewer. And first, the sharp edges of the electrode could potentially improve the efficiency of the phenomenon, but would also result in the instability of the system. And that's my conclusion. Thank you.
Question from 3.
I got a question for the reporter. Could you tell us what was the highest spinning speed with the typical voltage you use? What was the highest spinning speed?
Okay, so we can get 5.9
5.9?
time and turns in every second. So that is pretty high.
Was that 5.9?
Oh, here we represent here is 5.45, and we didn't, because the experiment we do is further, so we didn't put it on here.
Questions for all speakers. So I would like to know what it actually where is actually the torque coming from? So for the motor to rotate, there must be some torque. So where does the torque coming from?
So just like I just said in the slide, in the report, I think the torque comes from the repulsive and the attractive for current force, which given by the electrode, the positive electrode attracted to give it a speed to either faster or change the angle to let it slower, and also the
So I agree with the reporter that the negative electron will be repelled by the negative electron, be attracted by the positive electron. So this force will cause the rotor to rotate.
Well, I agree with both the reporter and the opposer that the main cause of the Coulomb force between the electrode and the motor. But I also suspect that because this question statement states that there is the main part of this problem is the corona discharge. I suspect that there's some components in the air surrounding the charged air surrounding the actual motor that can contribute to the spinning of the motor. But in our experiment, we are not able to really identify if this air around the motor had any effect.
Do you have any estimate for both contributions? You mentioned the Coulomb interaction and also the air.
Because we are not able to identify what exactly about the air.
Estimate you can do. You still can estimate. Did you do any estimation of the contributions?
No, we were not able to find like vacuum chamber to do experiments in, so we're not able to conduct this experiment.
So did you estimate the Coulomb force torque as I asked the reviewer? So
I think
does it compare? If you did, does it compare to the torque in general?
No, but I think that the main reason is just what I mentioned, and about the RNF of the air.
Okay, that is enough. Did you do the estimation?
To a torque?
Yes.
So we
with
have
the Coulomb force.
Okay, so we didn't put on this, but we do put a stick on the cup, which is here, and to pull a torque here, a stick here that is very light, the mass will be ignored, and then we put this point to
But that is measurement. Like, did you do the estimation?
Estimation. Sure, and we'll do it in the slide, which is on page 30. Page 30. Yes. So first of all, we calculate the angle that can really cause the force, and then we use the calculus to calculate the force from calculate this vector to this vector. Then we get this, but the angle, when the angle changes bigger, the larger
okay,
f
that
is.
is enough. Thank you.
Okay, so now that's it's time for jury to score. 674. The score for opponent. 77775. The score for reviewer. 66766. Okay, thanks to everyone. That's the end.